All right, so we want to talk about impulse now. So last video, I talked a lot about situations where the change in momentum is zero, right? This is the conservation of momentum, right? And this happens when there's no external forces, right? Okay. So the question is, how does momentum ever change, right? So how do you change momentum? You need a force, right? So honestly, from Newton's second law, right, you have a net force, that's a vector, is dp dt, right? You smush this around and you can convince yourself, hopefully, that the change in momentum is the integral of f dt, and we give this quantity a name, and it is impulse, and sometimes we call it capital J. Okay, so that is impulse. So what do we do with this kind of information? All right, anytime you see an integral of f dt, right, or integral of something d something, what do you think of? I hope that you think of an f versus t, and the area under the curve being that integral. So that shaded area is delta p, right? It's the impulse, right? And if we had sort of, here, let's go to another page. Oopsies. Right? If we had like a really, boring force for this amount of time, right? Then this would be the value of the change in momentum, right? Which you guys know how to do rectangles, right? It's just F times delta T, right? But obviously in this class, we can do funkier things like that, right? Where that is your delta P, but it's really the integral of F dt. Okay, so where does this stuff come into play in real life? Let's imagine I drop an egg, all right? And I could drop it onto concrete or carpet. All right, depending on if I want an omelet or not, I guess I have different choices. However, if we assume, right, so here's my concrete, and here's my carpet. Okay, so because literally you've been alive for this many years, that it will be less likely to break on carpet, right? So how does any of this relate to what we were just talking about? So in both cases, they're going to experience the same change in momentum, right? Because he's, got a certain speed when it comes down and hits the concrete or hits the carpet. So the delta P is the same. So if I were going to draw my F versus T for these, the area under each curve has to be the same. But what's the difference between carpet and concrete? Right? Carpet is smushy, right? It's got give. So what that means is that it extends the time over which the force is exerted, right? And it's it stops really quickly. With carpet, smushy things, or cushiony things, it extends the time, but the area in both cases is the same because they undergo the same change in momentum. And if you kind of think about what the average force is, right? The average force, if you have a longer time period, right? The average force for a longer time period is going to be smaller. And then, and literally you can write it like this. This is what I do with my like conceptual classes, right? So you've got a little tiny force, or sorry, a little tiny time on the concrete. And so you need a big force, but the carpet gives you a big time. So you only need a little force because the product of those has to be the same. So you can probably think about 12 different ways that this applies in real life. And I will pause to ask you to write 2 examples of other places you see this. Okay, so you might have come up with some of these things. So things like airbags, right? Really anything cushiony is doing this. It's extending the time over which the momentum is reduced, right? It's not that you have a different change in momentum if you have an airbag or not. You have to undergo the same change in momentum. It's just a matter of of how long it takes to do that. And then that'll determine the force required. Because honestly, force is the thing that hurts, right? When you bend your knees, when you land, right? So if you jump off of something high, you don't just, lock your knees when you land. You bend them, and that's to extend the time. Also, when you catch something, you don't just hold your hand there and let the thing just, touch your hand. You kind of move back with it. Honestly, like anything where you see someone doing parkour, right? They always have that kind of follow through. Okay? I do want to mention one thing that sometimes gets people confused. And you have F versus T, and you also have F versus position. Okay? And if you have graphs like this, these areas have very specific meanings, right? F dt, that is change in momentum, that's impulse. Okay? And hopefully you know that integral of f dx is work. Yes, exactly. Okay, so, just be careful looking at, what your x-axis is, because it might be a t, and these have different meanings. Okay? What's, particularly extra fun, right? This was a change in momentum here. Work, right? This was the net work. It's a change in kinetic energy. So they're not like entirely unrelated, right? This is, 1/2 mv squared, and this is like an mv, right? So there's a lot of the same information in here, but it is important to just be careful to know what you're talking about at any given time. The last thing I want to do with you today is let's talk about a ball bouncing off a wall and what's really happening here. So let's say it's coming in with an initial momentum, p sub I, and it leaves with the final momentum, p sub f. And let's just say this is a ball and it actually has the same speed. Oops, I'm writing in eraser all of a sudden. Okay, let's say that both the bouncing in and out are both the same speed. And you know what? Just for a thrill, I'm going to give you some numbers. I know you haven't seen me use numbers, but just wouldn't that be fun? Okay. And then let's name this angle, and let's say that's 60 degrees. Okay? So my question is, what impulse did the wall give the ball? Okay, so you say impulse and you're like, oh, cool. If only I knew the force and the time. Well, I don't. But I know, ooh, that's also equal to delta P. And there I have a chance. And look at here. I have 2 dimensions that I have to deal with. So let's break these bad boys up. So that is P, I, Y. And that is P final Y. That's P initial X, and that's P final X. So I think you can be quickly convinced that there is no change in momentum in the Y direction. And why is that? Because there's no force in the Y direction, right? What is this wall doing? This wall is exerting a force, right, on the ball, and it's to the left. Okay? And let me just pause for a second. All right? What is this ball? So this ball's going to hit a wall. And I showed you like a pivot thing, right? And it kind of like smushes and then comes out. This is kind of, this is when we talk about bouncing. Okay? What's really happening is that it's 2 parts. When the thing is moving to the right and the wall is exerting a force to the left, it slows it down. But then it actually throws it out again. Okay? And that force is also in that direction. So we get a force that slows it down, and then it has to keep exerting a force to throw it out again, to give it that that momentum in the other way. Okay? Okay, so you can actually see, and this was on the last page, sorry, these x components, Pix, has the same magnitude as P final x, right? And it's mv, right, here's your theta, mv cosine theta, right? If we plug in numbers, which I had in the other thing, it was 0.6, 2, and then cosine of 60 is a half. So we get 0.6, and then kilogram meter per second is the magnitude, right? So they have the same magnitude, but they have opposite signs, right? So if, I don't know, do you want to call plus that way? Sure, why not? So final minus initial, let's slap our vector signs on there, right? Our final is this way. So it's negative 0.6 kilogram meter per second minus, and then this is initial, so it's actually positive. So we get negative 1.2 kilogram meters per second for our change in momentum. Okay, that's our impulse. So if I, what does that negative mean, right? When I write delta P is F delta T, and sometimes we write T, sometimes we write delta T, we go back and forth. That sign, right, that negative sign is really the direction of the force that's causing the change in momentum. Okay? And I think that's a good place to stop.